In this video, part 3 of the Introduction to Simulating Nature series, I continue right where we left off last time. This time we're going to simulate the hydrogen molecule H2 using a quantum computer, or more precisely using Qiskit. Let's briefly recap. In the first two parts, I talked about how we can simulate nature with quantum computers, or more importantly, why we should do so in the first place. I showed the general workflow for simulating molecules to give a sense of motivation for why quantum computers are needed. Also in part 1, we looked at different application areas where quantum computing can make a real difference. Then in part 2, we went into more technical detail and discussed why classical supercomputers fail. Why, even with enormous computational power, there is still not enough for simulating quantum systems accurately. And that's exactly where quantum computers come in. And now I'll explain how we can actually perform such a simulation on a quantum computer. And here's what we will do. First, I'll define the H2 problem, what exactly we're trying to compute. Next, I'll give an overview of the approach we'll use, explaining in simple terms how we can obtain both the ground state energy and the ground state wave function, which is ultimately our main goal. Finally, we'll see how all of this can be implemented in Qiskit, using a quantum simulator. Of course, the same method could also be executed on a real quantum computer, but for this demonstration, we'll use the simulator. Let's start with the problem definition. We're working with the hydrogen molecule, H2, because it's one of the simplest molecules to understand and a great example for demonstrating quantum simulation. The H2 molecule consists of two hydrogen atoms that form a bond. Each hydrogen atom is made up of one nucleus and one electron. So in total, our system has two nuclei and two electrons. Our goal is to determine the ground state energy of this system and, more generally, its ground state wave function or state vector. That's ultimately what we're aiming to compute. I also want to say a few words about what an orbital actually is, because this term will appear several times later in the video. The classical idea that an electron moves on a fixed orbit around the atomic nucleus is not correct. In reality, we cannot say exactly where an electron is. We can't precisely predict its position because in theory it is everywhere at once. It exists in a superposition of many possible locations. When we perform a measurement, the electron appears at a specific place, and the chance that we find it there is given by a certain probability. That means we can only describe the electron's position in terms of probabilities. We can only say how likely it is to find the electron at a certain point if we were to measure it. Most of the time, around 99%, the electron will be found somewhere around the nucleus. Technically, 100% would include the entire universe, but that's not a meaningful assumption. An orbital is simply the region of space where the electron is most likely to be found, for example with 99% probability. So in short, an orbital is the space where an electron exists with high probability. And that's what we mean when we talk about an orbital. We will also make a few approximations along the way. However, these are not severe. Our final result will still be about 99% accurate. The small deviation from the exact solution is negligible for our purposes. The first one is the Born-Oppenheimer approximation. This approximation is based on the fact that the mass of the nuclei is much larger than the mass of the electrons, roughly 1,800 times larger. Because of that, we assume that the nuclei remain essentially fixed in space, while the electrons move around them. If we wanted a fully exact calculation, we would have to include nuclear motion as well. But for our case, that's not necessary. Even in full configuration interaction, FCI methods, which are mentioned in the previous video, this approximation is typically made. The second approximation is that we will work with the Schrödinger equation and not the Dirac equation. I won't go into detail here since I didn't mention the Dirac equation in the previous videos either. In short, the Dirac equation is the relativistic generalization of the Schrödinger equation. As I said before, the Schrödinger equation is really the heart of quantum mechanics, and it's perfectly sufficient for most cases. The Dirac equation becomes necessary only when relativistic effects become significant, which is not the case for hydrogen. For heavier atoms, however, one might have to use it. Next, we'll use a finite basis set, specifically the minimal basis STO3G. I won't go into the mathematical details of what STO3G means, because I want to keep it general here. For anyone interested, you can easily look it up. Just search for STO3G minimal basis. In essence, it determines how precisely we model the atomic orbitals. Finally, we'll also mention the active space approximation. You see this term appear later in the code. In principle, it means that we can restrict our calculations to only a subset of orbitals within the chosen basis. In this demonstration, however, we'll still include all orbitals, so this approximation doesn't actually affect our result. I'm mentioning it just for completeness, since you'll often encounter it in literature or in Qiskit examples. After applying these approximations, and there might be a few more minor ones I haven't listed here, we end up with what's called a 4-spin orbital model. In other words, we have two spatial orbitals, and each orbital can hold 2 electrons with opposite spins. We'll take a closer look at this structure in the next section. In this model, we're working with 2 molecular orbitals, or equivalently 4 spin orbitals. Now one orbital can hold at most 2 electrons, but only if those 2 electrons have opposite spins. Why is that? The rule in quantum mechanics says that no 2 electrons can have exactly the same quantum state inside one orbital. That's what's known as the Pauli exclusion principle. Since all electrons are identical, the only way they can differ inside the same orbital is through their spin. So if 2 electrons share one orbital, their spins have to point in opposite directions. One spin up, one spin down. Now, what is spin exactly? I also won't go into the details here because this video would get way too long, but you can think of spin as a kind of built-in property that particles have. It's a dual property. It can either be up or down. That's it. It's similar to electric charge. We say a particle has positive or negative charge, but we don't really ask why that is. We just know it has consequences. Positive repels positive, negative repels negative, and opposite charges attract. Spin is also a property that affects how particles interact. So the takeaway is this: you can't have 2 electrons in the same orbital with the same spin. That's why only 2 electrons per orbital are allowed. And they must have opposite spins, one up, one down. Let's come back to the STO3G basis. In this basis, each hydrogen atom is described, very roughly speaking, by a single function. This means we describe each hydrogen orbital with minimal effort, just one simple function. Using what's called the LCAO theory, linear combination of atomic orbitals, these 2 atomic orbitals combine and form 2 new molecular orbitals, a bonding orbital and an antibonding orbital. Why bonding and antibonding? Well, if the electrons are in the bonding orbital, they pull the atoms closer together, the bond gets stronger, but if they're in the antibonding orbital, the opposite happens and the bond weakens. So in our case, with H2 in the STO3G basis, we describe each hydrogen atom with one function, and together that gives us 2 orbitals, one bonding and one antibonding, or equivalently 4 spin orbitals, since each orbital can hold 2 electrons with opposite spins. If we were to use a larger basis like 631G, we would describe each hydrogen atom with 2 functions, and then we'd get 4 molecular orbitals in total, 2 bonding and 2 antibonding. But for now, with STO3G, we're keeping it minimal. I want to conclude by giving an intuitive idea of how all of this actually comes together. As mentioned before, the Schrödinger equation tells us the probability of finding an electron at a certain position. In other words, we ask the Schrödinger equation, where can I find these 2 electrons in the H2 molecule system? And the Schrödinger equation gives us probabilities for where the electrons can be found. If we take the H2 molecule, where the 2 hydrogen atoms form a bond, and give the Schrödinger equation all the information about the system, it will tell us something like this. With about 99% probability, you will find 1 electron somewhere in this region, that's one of the orbitals, or somewhere in that region, and that's the second orbital. And that's exactly what the Schrödinger equation tells us. So at this point, we've clearly defined our model. We've made our approximations, we've named them, and now we have the setup we'll use to calculate the ground state energy and the ground state wave function. As we said, we have 2 molecular orbitals, and each orbital has 2 spin orbitals. 1 spin up and 1 spin down. That gives us 4 spin orbitals in total. 2 spin up and 2 spin down. We also have 2 electrons in our system. To represent this on a quantum computer, we use 4 qubits, 1 for each spin orbital. Each qubit represents whether its corresponding spin orbital is occupied or empty. So if a qubit is in state 1, that means the orbital is occupied by an electron. If it's in state 0, that means the orbital is unoccupied. That gives us 4 qubits, and each qubit can be either 0 or 1. So in total, there are 2 to the power of 4 equals 16 possible combinations from 0, 0, 0, 0, no orbitals occupied, to 1, 1, 1, 1, all orbitals occupied. However, we only have 2 electrons in our system. That means not all of these combinations are physically possible. For example, 0, 0, 0, 0 can't exist because that would mean no electrons at all, and electrons don't just disappear. Likewise, 1, 1, 1, 1 can't exist either because that would mean 2 extra electrons appearing out of nowhere. So from the 16 possible combinations, several are ruled out. The only valid configurations are those where exactly 2 of the 4 orbitals are occupied, meaning 2 qubits are 1 and the other 2 are 0. And if you count those combinations, you'll find that there are exactly 6 possible configurations. The next step is to introduce a quantum circuit, an ansatz that puts our qubits into superposition and entanglement within a 16-dimensional Hilbert space. As I explained in the previous video, in a Hilbert space, each dimension corresponds to a basis state. In our case, those basis states are all possible combinations of our 4 qubits, from 0, 0, 0, 0 to 1, 1, 1, 1. Since there are 16 possible combinations, we have 16 basis states and therefore a 16-dimensional Hilbert space. By applying this quantum circuit, we prepare our 4 qubits in a state that is both superposed and entangled, effectively exploring this entire 16-dimensional space at once. Here I tried to make a simple sketch to visualize the Hilbert space. Of course, you can't actually draw a 16-dimensional space, that's impossible, but this is just meant to give an intuitive picture. I've drawn a few example states schematically. The dotted ones are just placeholders to show that it's not a realistic representation. In reality, also there would be 16 in total. At the top, I've written our state vector. This state vector consists of 16 basis states, ranging from 0, 0, 0, 0 to 1, 1, 1, 1. Each basis state has a certain amplitude, meaning a certain contribution to the total state. The green vector I've drawn represents our state vector, which lies somewhere inside the Hilbert space and combines all the basis states with their respective amplitudes. We now have all the tools we need to understand the overall process. There is just one thing I won't explain in detail here, and that is how the measurement actually works. I cover that later in a separate step because it's a bit more specific and slightly more complex. For now, I want to keep this part as clear and easy to follow as possible. So we have our vector, and this vector is somewhere in the Hilbert space. Our target vector, meaning the state that actually represents the H2 molecule, is also somewhere in the Hilbert space. We don't know what this vector looks like or where it is, and we need to find it. What we do now is apply our y-gate to manipulate our vector. For those who don't know what an r-y-gate is, just imagine that we're applying certain operations to our qubits that simply change the amplitudes of the individual basis vectors, which in turn changes our overall state vector in the Hilbert space. That's what we do. Each of these r-y-gates has a parameter. This parameter is randomly initialized at the beginning and determines how much and in which direction our state vector is rotated. So we start with an initial set of parameters, apply the r-y-gates, and our vector then moves to a new position in the Hilbert space. Next, we perform measurements, and from these measurements, we can calculate the energy. How exactly that calculation works, I'll explain later in more detail. The energy we get now is just some value. It's not yet the ground state energy that we're looking for. But here's the important part. This energy depends on the measurements we've made. The measurements depend on the amplitudes of the basis vectors, and those amplitudes depend on the parameters we've chosen earlier. Now we introduce an optimizer. The optimizer simply adjusts the parameters so that the energy becomes smaller. This process uses a gradient-based method. For anyone who's interested in how that works, you can check out part 1 and part 2 of my quantum machine learning series. After the optimizer updates the parameters, we repeat the process. We apply the r-y-gates to our qubits again, get a new vector, perform the measurements again, calculate the new energy, and then the optimizer adjusts the parameters once more to reduce the energy. We repeat this over and over until the energy converges toward a certain value. Once the energy has converged, we can assume that this value represents the minimum energy, and therefore the ground state energy. At that point, we can read out the vector that produced this energy, and that gives us both the ground state energy and the ground state vector. In this drawing you can see roughly what the process looks like. I've made a block diagram here to illustrate the overall procedure. On the right I've drawn the Hilbert space again. Of course, this time only with 5 dimensions, even though it's actually 16 dimensional. In reality it's impossible to draw, but this is just to give you an intuitive idea of how it works. The green vector represents our target vector, and I've also marked our starting vector. With each step we move a little bit closer toward the target vector, and we repeat this process until we finally reach it. Now, if we recall the Variational Quantum Eigensolver process, we vary the parameters, get a new state vector, perform the basis measurements, calculate the Hamiltonian from them, and from that the energy. We then use the optimizer to determine how we need to change the parameters, whether to increase or decrease them to minimize the energy. The optimizer adjusts the parameters, and we repeat this process. We continue doing this until the measured and calculated energy converges toward a certain value. That value, the point of convergence, is our ground state energy. Once we have found it, we can reconstruct our ground state vector from the measurements. And with that, I'd like to wrap up this video. I hope it was at least somewhat easy to follow and generally understandable. The reason I'm ending it here is that I wanted to structure this video series in a way that even people who aren't physicists or programmers can still follow along, at least to some extent. Of course, I know that it's still quite a challenging topic, but I hope I was able to give you a reasonably clear and intuitive understanding, even if you don't come from a physics background. In the next and final video, I go into a bit more detail about the measurement process, how exactly measurements work, and how we calculate the energy from those measurements. I'll also briefly discuss an alternative approach to the one we've used here, and then show how to implement everything directly in Qiskit. So if that sounds interesting, make sure to check out the next video as well. Thanks a lot for watching, and see you there.